Hi, my name is Iman El Ashkar from George Mason University. In this presentation, I'm going to talk about learning Bayesian networks using the R package BNLearn. Mainly, we'll be discussing constraint-based algorithms. This presentation is based on the paper Learning Bayesian Networks with the BNLearn R package by the creator of this package, Marcus Kothari from Genetic Institute, University College of London. The agenda of this presentation, we will be talking briefly about Bayesian networks and network structure, and on network structure learning algorithms, mainly constraint-based algorithms. Then we'll be going over BNLearn package implementation very briefly, and then we will be using the R software to test some of those algorithms on the data set bundled payment. Then we'll be going to conclusion of this presentation. Bayesian networks have been used in many fields in the recent years, like health service research and cancer research. The high dimensionality of the data in these fields required the development of several learning algorithms that reduces complexity while learning the correct network structure. BNLearn is an R package that includes several algorithms for Bayesian network structure learning using both discrete and continuous variables. And both constraint-based and score-based algorithms are implemented. However, score-based algorithms are not discussed in depth in this presentation. Bayesian networks are graphical models where nodes represent random variables and arrows represent probabilistic dependencies between them. The graphical structure G equals V and A of Bayesian networks is a directed acyclic graph, which we call DAG, where V is the node or vertex set and A is the arc or edge set. The DAG defines the factorization of the joint probability distribution of V, which is the variable set. We call it global probability distribution, into a set of local probability distributions, one for each variable. The form of the factorization is given by the Markov property of Bayesian networks, which states that every random variable directly depends on its parents. The correspondence between conditional independence of the random variables and the graphical separation of the corresponding nodes in this graph has been extended to an arbitrary triplet disjoint subset of V by Pearl with the D separation. That's why it got the name D separation from the direction dependent separation. Therefore, model selection algorithm first tried to learn the graphical structure of Bayesian network. That's why it got the name structure learning algorithms, and then it estimates the parameters of the local distribution function conditional to this learned structure. This two-step approach has the advantage that it considers one local distribution function at a time. It doesn't have to model the whole global distribution function explicitly. Another advantage of that learning algorithm are they are able to scale to fit high-dimensional models without incurring the so-called curse of dimensionality. So let's talk about structure learning algorithms. There are three types of structure learning algorithms: constraint-based, score-based, and hybrid. The constraint-based algorithms learn the network structure by analyzing the probabilistic relations using the Markov property of Bayesian networks with conditional independence test, and then constructing a graph which satisfies the corresponding D separation statement. The resulting models are often interpreted as causal models, even when they are learned from observational data, as stated by Pearl in 1988. While the score-based algorithms, they assign score to each candidate Bayesian network and try to maximize it by some search algorithms. Greedy search algorithms such as hill climbing and taboo search are a common choice, but almost any kind of search procedure can be used. Finally, the hybrid algorithms combine both the constraint based to reduce search and the score based to choose the optimal network. Let's talk more about constraint-based algorithms. They are all based on inductive causation algorithm by Verma and Pearl, which provides a theoretical framework for learning the structure-causal model. It can be summarized in 3 steps. First, we learn the skeleton of the network, which is the undirected graph underlying the network structure. Since an exhaustive search is computationally unfeasible for most data sets, all learning algorithms use some kind of optimization, such as restricting the search to Markov blanket of each node, which are the parents of this node, the children, and all the nodes that share a child with this parent, or what we call the co-parents. Second step, they set all the direction of the arcs that are part of a V structure, which is the triplet of nodes incident on the converging connection. Third, it sets the direction of the rest of the arc as needed to satisfy the acyclicity constraint. The BNLearn package implementation. The BNLearn implements the following constraint-based learning algorithms. We'll be able to see the function names in between parentheses here. The first one is grow shrink, or the GS function, which is based on the grow shrink Markov blanket. It's the simplest Markov blanket detection algorithm used in structured learning algorithm. Then we have the incremental association, or the IAM, which is a 2-phased forward selection algorithm. It's a forward selection followed by an attempt to remove the false positives. Then we have the fast incremental association, fast.im. It's a variant of IAM which uses speculative stepwise forward selection to reduce the number of conditional independence tests. Then we have the interleaved incremental association, inter.im. It's another variant of IAM which uses forward stepwise selection to avoid false positives in the Markov blanket detection phase. And last one, we have the max-min parents and children, which is the MMPC function. It's a forward selection technique for neighborhood detection based on the maximization of the minimum association measure observed with any subset of the nodes selected in the previous iteration. It learns the underlying structure of Bayesian network, but all arcs are undirected and no attempts are made to detect their orientation. The next big step in learning the network after learning the structure. So the first step, learning the structure, learning the nodes and edges or arcs of the network structure. And then the second step is learning the CPT, or learning the conditional probability tables of the nodes. There are several conditional independence tests from information theory and classical statistics are available for use in constraint-based learning algorithms, like mutual information and Pearson's association if we are using discrete data, or if we're using continuous data, there are linear correlation, Fisher's, z-test. So in general, to learn network structure, we have 2 ways. Either we ask an expert that explains how the data are linked together. Like for example, if we're using a medical data, we can ask a medical doctor. And the second way is to learn it from data. To learn it from data, we can do it manually, or we can do it automatically using the algorithms we'll be talking about now. So let's see an example. I selected the bundle payment data as an example to test the network structure, to learn the network structure using R. we know the network, so we will be using it as a baseline to compare what we get using the BNLearn package. In this data, we know, for example, and hospital leads to hospice, and hospital needs to bundle payment. Skilled nursing facility leads to occupational therapy, and occupational therapy leads to bundle payment, and see how accurate they are. What do they do? Let's go to R. So I compiled this simple BNLearn algorithms code here for you. First, we need to install .packages parentheses BNLearn. I did that already, so I can't install it again, but we need to call the library BNLearn. Then I need to set the working directory either by using this code set wd parentheses double quote, and you set your folder or working directory, or if you're using the RStudio, you can go to session, set working directory, choose whichever folder you saved your data, but I'd rather use this command here, and then I'll import my data, the simulated bundle data, read.csv, parentheses, double quotes, simulated bundled.csv, and I called my data D. I'd like to see my column names. They are right, CL, DME, PH, same variables or columns in my bundled data set. Then I would like to see to take a look at my data using the fix parentheses D command. And here's my data. I have 13 columns, binary. Also to check the class of the data frame, and the class of the columns or the variables. So when I first used this data, it was integer, and the BNLearn can deal with the integer data, so we have to turn it into factor or numeric using, I used this code here, D, my data, comma, the columns from 1 to 13 equals lapply, which applies this code on each column of my data, comma, as dot factor. So that will transfer. I will test it on column number 6, class D, column number 6, and I'll check it, and well, it turned it into factor. So now the BNLearn can deal with this data because it doesn't deal well with numeric or integer. So as we spoke earlier, we can learn the network either from data either manually or automatically. Let's see how we do it manually. I pretty much create an empty graph. So first I populate my variable names, and here are my variable names, and then I create empty dot graph including these variable names. Then I'm populating my R in this empty graph from these variables or nodes to these variables or nodes. So I'm telling my algorithm to populate an arc from DME to H, and from CL to H, and from P to H, from P to LTH, and so on and so forth. And then I'll plot it. Yeah, of course, unexpected string or something, but then I can plot it. This is not a very smart way of doing the graph,
of learning the network structure. So let's see what the GS, the grow shrink algorithm would do. This is the simplest. The grow shrink is the simplest Markov blanket algorithm, and using the code T equals GS parenthesis D, or your data name, whatever it is, from CL to H, P to H, except those two edges are not, from SNF to BP and RF to OT, these two edges are not directed. Otherwise, everything, all other arcs were correct. Then I will use the IAMP which is the stepwise forward selection spoke about earlier, and it looks exactly like the other one, like the GS, the grow shrink. So the network structures seem to be identical. If I'd like to test if they're identical, I use this code all dot equal parenthesis T, which is the GS, and T2, which is the IAM. Let's see if they're equal. If both networks are the same. True, they are actually equal. Now, let's see how many tests each algorithm used to learn the network. So the GS ran 503 tests to learn this network, and the IMB ran, let's see, the IMB ran 512 tests to learn our network. We can also try the unoptimized implementation of these algorithms using the end test parentheses GS D, or your data, comma, optimized equals false, or the other test, and we specify that optimized equals false, so to use the unoptimized implementation. Let's try the greedy search. T equals HC parentheses your data, and plot it. This one has a mistake here. One arc is reversed, but otherwise everything, arcs and the directions of the arcs, they all are included, so it's very accurate, but not as accurate as the GS and the IAM. So now there is the concept of blacklist and whitelist, and with the blacklist I'm telling my algorithm this arc here going from P to RF and the arc going from CL to H cannot be in the, I'm blacklisting those arcs. I'm telling the algorithm we can't have arcs between this node and this node, or this node, and then we run the grow shrink and we see the plot. So what I did, I told my algorithm not to include arc between P and RF. P and RF, yes, and it reversed it. Actually, let's see it here, because I compared both. This is the GS without the blacklist, and this is the GS with the blacklist. So without the blacklist, the P had an arc going to RF. When I blacklisted this arc, there is actually an association anyway between P and RF. So what the algorithm did, it reversed the arc. So there is no arc between going from P to RF, but there is an arc going from RF to, okay? And the same concept goes with the whitelist. The whitelist is the opposite. I am telling the algorithm there has to be an arc going from this node to this node. You have to include this arc in your graph. Let's see. SNF2, PBD. So it created a graph from SNF to PBD, and it wasn't there at the beginning. Blacklist and whitelist, and we actually can combine them both. T equals GSD, the data. Whitelist equals whitelist. Blacklist equals blacklist. And I can include as many nodes as I want, either blacklisted or whitelisted, and plot it. Let's see. Yes, it combined both. It combined my blacklist and my whitelist. Last thing I want to show is the debugging. We can see all the tests in action by running the debugging mode. So for example, for the GS, I will say T equals GS data, comma, debug equals true, and let's see what it goes. Well, so you can check all the tests, how all the algorithms included in this grow shrink, what happened here by running the debugging mode, running the debug equals true. Then of course we can log the learning process, this learning process for future reference if you want, using this code here, sync, parentheses, file equals, call it whatever you want, and then T equals GSD, debug true, so it gets you all these steps in the algorithm, and then sync, parentheses, empty. For future reference, use the unoptimized version if something seems wrong, and or we can use the unrestricted version using this code, because sometimes inconsistencies trigger errors in the strict mode. So use T equals GS data, comma, optimized equals false, comma, strict equals false. So we're disabling both the optimization and the strict. And debug true, and you plot it. Well, it almost gave almost the same result. Last thing I wanted to say about the BNLearn, it actually allows me to set arc if I want to set arcs, drop dot arc. So it allows me to set, drop, or reverse arcs. Conclusion is network structure learning algorithms are helpful to provide fast and convenient way of learning structure. Automated network structure learning may not work perfectly because sometimes they may not expect all edges, or sometimes they learn the wrong direction. So the best practice is manual network structure learning and algorithm learning together, combining both together, using the whitelist and blacklist, and using expert input as a reference. Here are my references. Thank you so much.